So you've watched me attempt to fly to and land on the moon, and you've watched the excellent video showing how the Keplerian elements define a elliptical orbit around a planet. That's sort of the basics, but I want to talk about some of the problems that you're going to run into trying to complete homework 3, or at least the things that I think are going to be the tricky parts. Now, the first thing that's slightly a tricky part is the landing script. The idea is that we have the ground, we have your rocket with legs, and your rocket with legs is coming down, and we want it to land on the ground, not crash into the ground and explode. However much crashing into the ground and exploding is more fun, that's not the goal. The goal is to land the rocket safely. So as the rocket comes down, we want it to slow down, and we want it to be going at speed 0 when it touches down on the ground. Can't be going exactly speed 0, but generally if you're under like 0.5 meters per second, your rocket is unlikely to explode, especially if it has landing legs. In fact, if it has landing legs, you might be able to get away with it going 1 meter per second. Now, the first sort of solution that seems like it makes a lot of sense is you want to pick that point in time to start burning your engine such that you get to burn your engine at full throttle, and as you touch down on the ground, you can turn your engine off. You're at speed 0 as you touch down. That strategy of waiting till the last possible moment and then burning at full throttle is called a suicide burn. It's the most efficient solution, but it's also a little bit tricky because you have to deal with the fact that like the mass of the rocket is going to decrease through the burn, which is going to increase your thrusts. At the same time, you are getting closer to the planet. That means that the force of gravity increases as you come down, and so your acceleration due to gravity is going to increase. So you have to get all your math, you have to figure out all of the pieces and get your math right to estimate the suicide burn correctly. A simpler strategy is just to say in stages, at this height we want to be going 100 meters per second down, at this height we want to be going 50 meters per second down, here we want to be going 10, and then at this height we want to be going 1 meter per second down. And you can even either have this be like a smooth continuous function, or you can have it be a just step function, and then you can use some sort of control loop to decide how much you want to burn to slow down, and then once you get to your target speed, you can throttle down and keep burning to make sure that you don't accelerate. So you're trying to counteract the force of gravity as you go down. That's a strategy. And probably the optimal strategy is somewhere between those two extremes. Well, I mean, the optimal strategy is the suicide burn, but the most effective strategy for trying to quickly write code that will effectively solve the problem is some intermediate step. Now, I want to give a sort of concrete couple of numbers just to sort of help think about the problem. So if we are currently going, so let's say our current altitude is 100 kilometers, and our current speed, our velocity is going down at 1,000 meters per second. So assuming we don't accelerate further, and we're in gravity, so we're going to accelerate further if we don't do anything, but assuming we like burn the engine to exactly counteract gravity, if we're 100 kilometers up and we're moving down at 1,000 meters per second, then we're going to hit the ground in 100 seconds. Now let's further imagine that acceleration due to gravity is 10 meters per second squared. So every second that we don't act, our velocity is going to increase by 10 meters per second down. Or or sorry, the first second we don't act, it's going to go by about 10 meters per second down, but then we're going to go faster and faster because we're accelerating. Let's also say that we have thrust such that we can go 20 meters per second squared if we burn our engine. That means that we have sort of net thrust that we have to work with to slow down of 10 meters per second squared. Now, if we were to start burning right now to slow down at 10 meters per second squared, starting velocity of 100 meters per second, or sorry, 1,000 meters per second, it's going to take us 1,000 divided by 10, or 100 seconds, to get to velocity 0. So we're currently at 100 seconds to impact, and we're at, assuming we don't accelerate further, and it will require 100 seconds to slow down. So as a sort of initial estimate for when to start burning, my initial estimate for when to start burning is right now. That's going to end up stopping us a little bit early, because as we slow down, we're going to be going slower, which means it will take less time to, it will take more time to get where we're going. So if we start burning this rocket right now, we're going to stop somewhere above the surface. In 100 seconds, we will come to a stop, and we won't have landed yet. The question then is, how can we decide exactly when to start burning? And that is sort of the challenge here. One thing that we can do is burn at less than full thrust a little bit here, trying to maintain a time to impact with no further acceleration of some constant amount of time. So maybe we burn so that at our current velocity it will take us less than 100 seconds to impact, try to reduce this number, and try to make it so that when we get to 0 seconds to impact, we aren't moving. But probably worth playing with the landing script and playing with the math a little bit. That's largely what I want to say about landing. Our second problem that we have to deal with here is how to set up that maneuver node and the preconditions that we want to deal with are we have Kerbin, we have the moon, we have our orbit, with our spaceship. The first thing that we want to assume is that we are coplanar with the moon. If we're not coplanar with the moon, then it's going to be annoying to come up with a transfer orbit. We could do super fancy math and do a transfer orbit that didn't require us to be coplanar, but we can't draw that on the whiteboard, so I don't want to deal with it. I mean, we can't easily draw it on the whiteboard. So first step is to be coplanar, and to be coplanar, if you're not, you find your ascending or descending node and you burn up or down to change your inclination to match your target, and then you're coplanar. So now we're coplanar with the moon. The next thing that we want to do is we want to figure out what burn we need to do in our prograde direction at some point in order to get our transfer orbit. And the transfer orbit that we're going to produce is going to have an apoapsis which is going to be equal to the sort of orbital height of the moon. Now, I think the moon has a circular orbit in this case. If the moon had a non-circular orbit, this would be trickier because we'd have to have the apoapsis of our transfer orbit match the altitude of the moon at the intercept. But the moon's orbit's circular enough that we can ignore that for the moment. So the tricky part then, the only tricky part, is to calculate when to do the maneuver. And to do that, we first need to figure out what this transfer orbit looks like, and then we have to calculate what the time is going to be for our ship to go from when we did the burn around to apoapsis in that burn. And then we can project forward where the moon is going to be. And it doesn't matter, like, this time that it's going to take for us to go from our burn to the moon isn't dependent on where we do the burn. Where we do the burn around Kerbin, it's going to be the same shape ellipse. The question is just which direction is it going to be tilted in. That's what we're trying to solve. So once we figure out what the shape it is and what the time is going to be, we're going to predict forward where the moon's going to be. We probably in KOS can do that by using the prediction commands and actually passing into the prediction command an orbit, or sorry, passing in the moon and asking for what its position will be at a time in the future. That will let us predict its position. If that doesn't work, we may have to do the arithmetic of figuring out its orbital velocity or its orbital period, and then calculating how far it's going to sweep. Either way, that's math that we can do. But once we know where the moon will be after the burn, we can then decide to put the burn at the angle around Kerbin such that when we do the burn, it will set up the transfer orbit so it actually transfers us into the moon's sphere of influence. And for the purpose of this exercise, we can consider that where the rocket is in orbit around Kerbin in the single orbit where we're going to do the burn doesn't matter. The orbital period for a rocket in low Kerbin orbit is 10 or 20 minutes, maybe half an hour to do a full cycle. And 10 or 20 minutes isn't going to let the moon move far enough that we're going to miss it as the result of burning 10 or 20 minutes early or late. So we figure out how long it's going to take to do the transfer. We figure out where the moon is going to be after that amount of time, assuming that we're going to do the burn 0 seconds in the future. We're then going to figure out where, if the moon is going to be here at whatever angle off Kerbin, we want to do our burn opposite from that, so that our apoapsis will be where the moon is. Then we set our maneuver node there, and then we can just run our maneuver node execution script to do the right thing. So that's the basic plan. To review my plan for doing a moon mission is the following steps. First, we launch to low Kerbin orbit. Then we plan a burn to transfer orbit. We plan and then execute a burn to transfer orbit. Then we do a burn to circularize at the moon. Then we do a burn to set up for landing, burn to drop our orbit so that we're going to hit the ground. Then finally we land, which I talked about before. So good luck on homework 3. The sooner you get started, the more time you'll have to deal with all these problems, and the more opportunities you'll have to come up with good routines to pull requests to the library Git repository that I set up for bonus points and to help your fellow students, because some of these individual problems, especially with calculating locations and orbits, are moderately annoying. So have fun.